All right, the next we're going to talk about how we can show what happens when the reaction takes place, and why they take place, and why some are faster, why some are slower. It's going to be using something called a potential energy diagram, also known as a heat content diagram. Well, I have many other names as well, but this is what we're going to be dealing with. When a reaction takes place, collisions occur. And when that occurs, if they occur at the right point of each molecule, they're going to break bonds apart. Now, bonds are the result of energy being shared between two atoms. When that bond is broken, the energy is released into the environment. And then, almost as soon as it's released into the environment, the resulting particles left over form new compounds and take some of that or all of it, that energy, to create the new bond. Sometimes taking more than they release, which is called an endothermic reaction, one in which they take some of it back and there's heat left out there. Those are called exothermic reactions. If you can feel heat coming off, that is an exothermic reaction. The word exo means outside heat, outside of the system. Endothermic means within the system, heat within the system. And so, if something feels cold, it means it's been taking a lot more energy into it than what it gave up in the first place. How do we show that, though? Well, we're going to be using that diagram here. The heat content diagram looks something like this. And let's take this scenario right here. Let's suppose that nitrogen and hydrogen collide with each other, creating the compound ammonia. And when that occurs, then we have a delta H of negative 80.8 kilojoules per mole. Now, in this energy content diagram, this is a very generic look at it. We're not looking at specific values. It's more of a relative value kind of thing. But we're saying here that the amount of energy stored here is greater than the amount of energy stored here. So when the collisions occurred, all that heat was released and some of it was taken back in, but the difference was this. So in effect, what really happens is you get kind of this thing right here taking place. Now, this distance between the two levels, these are the reactants. And the reactants here are N2 plus 3H2. And the products are over here, which are 2NH3. And the amount of stored energy decreases dramatically. How dramatically? Well, according to this diagram right here, that change in heat levels from this level to this level is negative 80.8 kilojoules per mole. And that is described in the delta H. So this difference of platforms is your delta H. Now, from here to here, from this point right here to the top of the hump, that hump is where something has to be created in order to allow it to fall back down over here. So the energy is given off and stuff is created here, it's really unstable, and then it reforms something else. We call that a transition state. In organic chemistry, a lot of times this is what we call intermediate states. All right, and as soon as that creates, this just falls down. All that heat is released. This right here, the difference from the reactant level to the top, is called activation energy. That's the amount of energy we had to get in order to get that reaction to take place. It's kind of like a chemical kick in the pants. Get going. Let's go. So that value is always positive. It's always going to be higher than the reactant level. In this case, it's 45.0 kilojoules per mole. Now, all of these are numbers that are inherent only to the reaction you're looking at. We have a whole chart in the back of the book that helps us predict what these are going to be, but they're never the same. All right, so this is what an energy contact diagram looks like. And again, I'm going to emphasize, reactants start, products end. In the middle, the hump is created, goes up and then down. This difference of levels is your delta H. This difference between the reactant level and the very top is your activation energy. This is how you draw a heat content diagram or potential energy diagram. Now, it is possible to go the other direction. So we can start with ammonia and force it to go back the other way. So the NH3 that creates or decomposes into N2 and 3H3. When that happens, the delta H flips. In other words, we've taken these two levels and we've done this. So now we got here, and I'm going to do this in red to show the difference here. Here are the reactants, which is 2NH3. And the reactants are always first, because that's how you start a reaction. You have something to react with. Hence the word reactants. You're going to produce something that's your products. And that's going to be our nitrogen and hydrogen gases mixing together. But they're at the same level, here and here. It's just that they're now on different locations in the chart. Now, this hump right here is going to be the same height as the hump here. So right there, we'll say right about there, is where our hump is going to be, and we're going to go up and then down. Okay? Now, again, the difference, let me use this color for this one. The difference in these two levels is, again, from your reactants to your products, that's your delta H. It's going up, it's taking energy from the environment in order for this to exist, and it's going to be the same difference. You see the difference between the two levels? It's just that this is going down and this is going up. So instead of negative 80.8, this is going to be positive 80.8 kilojoules per mole. Okay? Now, activation energy. Now the activation energy, we said, starts from the reactants to the top of the hump. Well, the reactants are way down here and the hump's way up there. So that means this right here is your activation energy. Well, like I said, it's always positive. But in an endothermic reaction, this is endothermic, this delta H is positive. In an endothermic reaction, that is going to be huge. How huge? It's going to be the sum of the positive value of this, from 80.8 from here to here, and the 45.0 we said is going to be right here. So that's going to be equal to 80.8 plus 45.0, and that is going to be equal to 125.8 kilojoules per mole. That is a tremendous amount of energy to start a chemical reaction, which is why a lot of endothermic reactions do not occur in nature. Very few do. Most chemical reactions in nature are exothermic because it doesn't require much energy to get started, at least in comparison to the endothermic, and that energy is coming from the sun. This has to absorb energy in order to get going, and that's a lot of energy. So that's how you do reverse reactions. Reverse reactions are the same reactants and products, only switch around. Reactions now become the products become the reactants, and it really helps to draw these braces that I put in there so you can see the difference. All right, so that's what happens when you have an exothermic reaction. Now let's take a look at what happens when you have an endothermic reaction. So again, we're going up from here to here, and it's going, the reactants here are right there, 1/2 N2 plus O2, that's your reactants. And the products then are NO2, there's the products. NO2. Okay, and the activation energy is 52.5. Well, let's identify delta H right here. That's the difference between these two, and since it's going up, that's the positive. So that right there is your delta H. And that delta H then, we said is equal to 30.3 kilojoules per mole. Okay? Now I'm going to use green to show this going up, and it's going to go up slight about 2/3 of the way up past this, so that means go way up here and then come down. Okay? So your activation energy is from the reactants to the top of the hump, remember? EA equals 52.5 kilojoules per mole. Okay? So that is what the endothermic reaction will look like, given this information. Now let's look at the reverse reaction, which is going to be an exothermic reaction. So now we're going to go back in this direction right here. So the NO2 is going to be your reactants. And the 1/2 N2 and O2 are going to be your products. Okay? So, let's first of all identify where our delta H is, and again, it's the difference between the two levels. Right to that level, delta H. And we said that that is now going to be, since it's going down, got to be a negative 30.3 kilojoules per mole. Okay, now we know that hump's going to be up here, so I'm going to put that right up there, say right there. So, go up. I hate it when that happens. You go up. Wow, didn't like that, did it? That's what we did. Okay, anyway, whatever. And now, I'm going to have fun getting rid of this thing. This is just good, alright. Alright, so that means then, so that is my new activation energy from the reactant up to the top of the hump. And that's going to be 52.5 minus the 30.3, and that gives us 22.2 kilojoules per mole. And again, remember, activation energy is always positive. You can't have a negative activation energy. So, that's what your diagram is going to look like in practice problems. And right here, 61, 62. Good luck!